Using the Arrhenius equation to calculate K at one temperature from K at another. So we have met the Arrhenius equation. So K equals A, the frequency power, times e to the power of minus EA, which is the activation energy, over R, the gas constant, times T. So what we can do as a neat little trick is do a ratio between K2, the rate constant, at time 2 or temperature 2, over K1, the rate constant, at the initial temperature, and then we can do AE to the power of the activation energy over RT for K1 and K2 for temperature 1 and temperature 2. So that'll be AE to the power of, I'm going to need more space here. Woo! More space required. Minus EA, activation energy, which is going to be the same, over R. Then let's call that T2 for temperature number 2, and then over AE, to the power of minus EA, activation energy, over R times T2. Let's tidy that up a little bit so we can see what we're doing. So we can actually simplify this quite a bit, okay? Because A, the frequency factor is going to cancel out, and EA over R, well, activation energy is just going to stay the same, and R is the gas constant, R. So we can actually take those out of the equation in order to simplify it a little bit. So we can do K2 over K1. Sorry, that's a big K. I meant to write a little K there. K2 over K1 is going to be, and don't forget the minus, if we take that EA out, it's going to be e to the power of, let's do it up here, minus EA over R, and then that will be 1 over T2 minus 1 over T1. So we simplified that a little bit. That's supposed to be a capital R. We can make that a little better because e to the power of all that jazz is just a little bit too much. So we're going to do the natural log of both sides to get rid of that pesky e to the power of. So the natural log of K2 over K1, so parentheses advised, K2 over K1 is going to be equal to minus EA over R times 1 over, whoopsie, T2 minus 1 over T1. So when you're stuffing numbers into this, you do have to be a little bit careful with parentheses, etc., especially because we've got a minus sign in there, etc. So definitely do proceed with a little bit of caution here. Let's get some of these in here so it looks a little bit neater. There we go. All right, so this is what we're going to use. So in this case, what do we have? Well, we have our activation energy. All is good. We have our rate constant here, so that is going to be our K1. We have our temperature that corresponds to, so that is going to be our T1, and then we're asked to find the rate constant at T2. So we're solving for K2. Little caveat here, we have to think about dimensional analysis, okay? What is the gas constant? Well, in this case, we're going to use R equals 8.314 joules per mole per Kelvin. So looking at that, we are going to want our activation energy not in kilojoules per mole, but joules per mole. So we want to convert activation energy from kilojoules to joules per mole. And we do not want temperatures in Celsius. We're going to want temperatures in Kelvin. So let's do a quick little conversion. So my activation energy will be 77 kilojoules per mole. Convert kilojoules into joules. Yes, I know you can do it in your head, but I'm going to show you how to do it properly. Every 1 kilojoule is 10 to the 3 joules, or 1,000 joules if you prefer. So that is going to be 77,000 kilojoules per mole. I've just realized I should probably move that somewhere so I can show the whole shebang. Like so. Okay, so then we're going to do the same with our temps to get them into Kelvin. So T1 was 210 degrees Celsius, so add 273.15. We'll get that into kelvins, and that is 483.15 kelvins. Rinse and repeat for T2. T2 was 234 degrees Celsius. Oh, sorry, I should have put a 0.0 on there. Now my box isn't big enough. Add 273.15 kelvins, and I get 507. If I could type 0.15 Kelvin. Okay, so now we can stick everything into the 2-point version of the Arrhenius equation right now. So ln of K2 over K1. I'm just going to forget about you for a minute, right? Just stay there. Don't move. Is minus EA, so that's minus 77,000 kilojoules per mole, divided by whatever R is, which is 8.314 joules per mole per Kelvin. So we can see right away that our moles and our joules not kilojoules, are going to cancel out. I don't know why I've written kilojoules there as well. What a silly numpty I am. That is talking and typing right there, isn't it? Right. Of course, the whole point of doing that was to convert that into kilojoules per mole, right? So we're just going to ixnay on that. Joules per mole. That's exactly what I was trying to do, right? So because these guys cancel up. Oh, I quite like that red X. I might come back to that. Okay, so I digress. So our joules per mole are going to cancel like so. Okay, so then we are going to multiply that by my 1 over T2 minus 1 over T1. Again, if you're putting this in on your calculator with inverses and blah, 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 you are probably going to have to be super careful with using more parentheses than you think you need to use. That's like the number one way I see people stuffing this up. 483.15 Kelvin. So again, we can now see our Kelvin are going to cancel and we're going to end up unitless. What beauty. So bye-bye Kelvins. Okay, so that whole right-hand side of the equation is just going to turn out to be a number. Boo, 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 boo. It's about minus 0.907, and we're not going to be freaked out by the fact that there is a minus in front of it because there's a minus in front of the EA. Okay, so now we just got to get rid of this ln. We've got ln K2 over K1 equals 0.907. So how do we get rid of a ln? We do e to the power of both sides. So K2 over K1 is e to the power of whatever number you get for the whole right-hand side of the equation there. E to the power of minus, wherever it's 0.907. So again, that's just going to be a number, right? That shakes out to be, what is that? 2.477. I'll keep a few sig figs, blah, blah, whatever. So now we just have to solve for K2. So K2 is going to be e to the power of whatever that was equals 2.477 times K1. So your answer is going to come out in whatever units you have for K1. So that's going to be 2.477. Sorry, I wrote that down wrong. 77 times K1, which was given to us in the question as 0.47 per molarity per second. So that's what our answer is going to come out to be. And I got that is 1.164 per molarity per second. Let's make that bigger. And that will be my answer. So, sig figs is a 2 significant digits, so I guess I would round that to 1.2 per molarity per second. So that is how you deal with calculating K at one temperature from K of another.